All right, well, hello, everyone. My name is Joseph Crandall. I'm going to be presenting this morning on topological quantum computational input-output. This is for a University of Florida ECE PhD written qualification exam presentation and Q&A. The committee is Dr. Dalir, Dr. Hadari, Dr. Sorger, and Dr. Guo. And I'm Joseph Crandall, and it is October 29th, 2025. So I'm going to cover this topic in roughly 3 sections. These correspond with the chapters of the paper, starting with an outline of quantum information encoding modalities. And then from that, use it as a motivation into topological quantum computation theory. And then from that theory, we will apply it to the latest research concerning a superconducting indium arsenide aluminum device. So first, our quantum information encoding modalities. So I will not say this is fully encompassing, but these are some of the most common modalities. So I'm going to discuss superconducting circuits, photonic networks, spin qubits, neutral atoms, trapped ions, and then finish with a bit of a motivator, referring to John Preskill's statement on noisy intermediate scale quantum and where we are in that progress and where topological qubits can fit into that story. So for superconducting circuits, an overview, the encoding is generally done at Cooper pairs, energy levels of Cooper pairs on opposite sides of Josephine junctions. And you'll see in the topological implementation with Majorana fermions at the phase boundary in a superconducting wire or at the core of vertices and strong magnetic fields. Generally, the positives of superconducting circuits are high coherence and processing speeds, relative ease of manufacturing with existing CMOS, long-lived qubits and resonators, and generally capable of high-fidelity gates. And some of the cons or the challenges are the calibration. We'll talk about that specifically in the topological case, as well as the control electronics, the requirements for cryogenic near absolute zero temperatures, and then fidelity decreases as qubits and gates increase, although I wouldn't say that's unique to superconducting. And the figure that we're looking at here, we're going to come back to this quite a few times, but this is part of the interferometric setup for the topological multi-quantum dot superconducting wire that we will discuss later. Next, photonic networks. So often you are encoding the qubit in either the polarization of the photon or in actually the path that the photon travels in the network. The pros here are you have possibilities for large amounts of quantum entanglement, massive quantum entanglement, and you have generally coherence over long distances, room temperature operations, and also compatible with mature semiconductor manufacturing technologies, especially with the development of PICs quite heavily in the last decade or so. On the negatives, you have photon loss during the computation, and that either has to be accounted for and then regenerated. More decoherence through interactions with the environment. Obviously, decoherence is an issue for all of these modalities, but this can be specifically issue with waveguides. And then also 2-qubit gates tend to be probabilistic rather than deterministic. So fully digital implementations of photonic networks can be trickier, and you can see implementations that are more of a annealing or sort of analog computing versus digital. For spin, and also just to go through, this is a publication from Nature in 2025 for scaling and networking of modular photonic quantum computer. So going through the architecture for that. For spin qubits, we are encoding it in probably the most straightforward modality, the spin degree of freedom, either an electron or neutron, which is a natural 2-level system. The pros are they are high density, long coherence times, also utilize traditional CMOS for the most part. Cons are the challenges in fabricating very large arrays, also precise control electronics, and also increased cooling challenges dealing with heat dissipation. And I've included a review from 2023 of the maturation of a few different spin qubit devices. So this loss Divenzo device, a donor, a single triplet, and exchange only. You can see earlier and late stages devices that have been developed. Next, we have neutral atoms. This is usually done through some form of a magneto-optic trap, and then the qubits are encoded in those energy levels. Also long coherence times for positives, and they tend to be encoded in stable ground states. We're also going to talk about the ground state that we are trying to achieve in the topological example. And then the cons, also challenges with scaling the number of qubits while maintaining coherence, and then dealing with the finite lifetime of the Rydberg state. And this is from, I don't think it's a review paper, it's a specific system from 2022, multi-qubit entanglement. And you can see the different Rydberg levels that the neutral atom is going up to, as well as the 2D array and the excitation mechanism. And then finally, we have trapped ions, also encoding in 2 energy level states of an ion. Pros here are low energy rates for small 2 qubit gate systems, lower cooling requirements compared to at least some of the superconducting modality implementations, and high fidelity due to physical maneuverability of the ions. And then the cons are the slow gate speeds. This is probably its biggest con. Challenges in creating entanglement across multiple qubits, and then issues with fidelity in terms of as distance between the ions is increased. And then I've included another Nature publication here of both a schematic of the stack of the trapped ion composed of an optical modulator, electronics, waveguide, single photon detector, interlayer vias, interlayer dielectrics, transparent conductors, and current carrying metallics. And then also just a simpler diagram of the qubit control between the states, Coulomb repulsion, the laser cooling, detection, and the trap potential. So after going through all of those modalities, I think it's good to look at where we are, both in comparison to classical computing and also within the realm of qubits for these different modalities. In the framing of noisy intermediate scale quantum, which, as I was saying earlier, John Preskill coined in 2018 to talk about this current phase where certain algorithms, Shor's being the most canonical, are outside of the reach of current quantum technologies just due to the quality and quantity of qubits available. And it's important to try to understand what algorithmic breakthroughs will be available in the order of magnitude of qubits that are currently available. And you can see we do have quite a long ways to go. If you look at sort of classical 2 nanometer process transistor densities, they're at roughly 10 to the 8th transistors per millimeter squared, or roughly 100 million per millimeter squared. And then your classical logical devices now are in the hundreds of billions of transistors, getting close to a trillion. And then your leading edge supercomputers are now in the exascale. So obviously it's very important to identify algorithms that can utilize some form of a polynomial time complexity speed up compared to either a sub-exponential or an exponential classical implementation. But we can see as of right now, if we look at some of the leading devices in the mid 2020s, we see some of the modalities that are common: neutral atoms, superconducting, photonic, continuous variable. And then I've included at the bottom the device that we're going to talk a little bit more about, the Majorana 1 device from Microsoft, which is superconducting topological with only 8 qubits, so quite a ways behind the leading devices. But it's very important to draw yourself, or to focus on probably one term on this table, which is physical qubits. And that's because all modern implementations of quantum algorithms use some form of error correction, where you implement one logical qubit from some multiple of physical qubits. So any technology that can drive down that ratio of physical to logical qubits and maintain it over multiple orders of magnitude of scaling is potentially very powerful. So this is obviously, I don't know if anyone from the research side of Microsoft Research would admit to this, but it's definitely a public Microsoft goal to scale the topological architecture to roughly 10 to the 6th or a million qubits. And we can talk about why that is a possibility and could help this technology surpass some of the others that are a little bit further along. So now that we have discussed the modalities, we can talk about the topological quantum computation theory. And just for context, most of the device content that we're going to discuss is pretty current from the 2025, 2024, 2023, but most of the theory was worked through in the late 1990s and early 2000s. So there's slight changes in nomenclature as we go through the theory into the implementation, but the core concepts are still the same. So to break this down, we are going to talk about the core ideas in topological QC theory, which are not totally inclusive, but the main ones are anyons, topological functors, the Jones polynomial, and Witten-Chern-Simons theorem. And just as a fun aside, that Simons is actually Jim Simons, or if you know who that is, James Simons. Then we're going to discuss not specific to topological, but general concepts in quantum computing, so qubits, quantum gates, quantum circuits, and bounded error quantum polynomial time. Then we're going to talk about the type of anyons that we need, non-abelian anyons within the fractional quantum Hall effect. Then we'll talk about K-code and that neighborhood, and then the ground state transport braid group projection process of how we identify that K group neighborhood, and then the way that the projection occurs. And then finally, just a general algorithmic understanding of braiding, fusing, and evaluation. So the rough steps that go into any topological QC device. Okay, so what are anyons? They're a quasi-particle, common in two-dimensional systems. They have statistical properties intermediate between fermions and bosons. There are two general types, the abelian anyons, which behave in a similar fashion to bosons. They have, through an exchange of anyons, you see a quantum state multiplied by a phase factor. But what are more important for us and are actually critical are non-abelian anyons, where their exchange creates a superposition of multiple states, which is where the quantum information is encoded. The concept of a topological modular functor is a mathematical structure, and it maps surfaces to finite dimensional vector spaces. For our case, this would be Hilbert spaces, and they need to be unitary. And then the idea of cobordisms, or surface gluing of those linear transformations. So we can encode the algebraic geometric data of this 2D conformal field theory, and then this 3-dimensional topological quantum field theory. And as we progress through this, we'll sort of see how these 2-dimensional fields or disks propagate through time, and how those anyons move through that adiabatic transport process in that over that time. And most importantly, we need to make sure those are unitary modular functors, because those ensure probability conservation, which is critical for any quantum computation. Next is the Jones polynomial. And the most important thing about this is that it's a knot invariant that assigns a Laurent polynomial to each knot or link encoding its properties. And the most important concept here within knot invariance is that we want to be able to project and understand a knot from multiple slices, multiple dimensions, multiple projections. You could have a very high dimensional knot, and in a 2-dimensional view of that knot, it can be very difficult to understand if that knot is the same or different from another knot, or if you have multiple knots, multiple strings together in a braid group. So being able to identify something that does not change regardless of the projection you're taking is this knot invariant. And if we can calculate that knot invariant by transforming it into a polynomial, then we have a way to calculate how these knots, or as we'll talk about, braid groups, change over time. And this is just an example of, if we look at these three, L plus, L minus, and L0, we can see that they're identical except for how they cross. So crossing over, crossing under, and not crossing. And regardless of how we look at the projection of this nut, we can find that these crossings don't change. And then we can calculate the polynomial off those crossings. And this gives us a way to understand how this is changing over time. And then that all comes together in the Witten-Cherns-Simons theory, which is a special unitary 2 group, three-dimensional topological quantum field theory that describes how these non-abelian anionic models, this anionic model for topological quantum computing. And it also, I'm not going to talk too much about Yang-Mills, other than it's another quantum field theory for nuclear binding, and also is gauge theory and has a special unitary group, but it incorporates the Yang-Mills theory and provides that framework for understanding the behavior of these non-abelian anyons. So those concepts we're now going to map back to the core concepts of quantum computing. So within quantum computing, we have qubits, gates, circuits, basis, as well as universality, probabilistic outputs, and then bring it all together in BQP, or the class of algorithms of bounded error quantum polynomial time. So discussing qubits, these are expressed as two-dimensional complex, in a two-dimensional complex vector space, a Hilbert space. We can define gates and circuits through their tensor products. In this example I just wrote out, we have a spin 1/2 particle, consists of a sequence of k gates that apply to individual or paired tensor factors. They perform a quantum coherent interaction where the relative phase between the components of the superposition are preserved, and the gate is unitary transformation. The basis, which is how we relate it back to usually a standard basis of 0 and 1. And this reference basis, which is also orthonormal, this reference basis is important for encoding classical information, because when we take a measurement of that computational basis, we can observe the qubit being in either a 0 or 1 state with some probability. And that's why we describe it as a fixed basis, and then we apply superpositions onto that fixed basis here, just alpha and beta. And then for qubits, obviously, we can scale this out, and this is also written in bracket notation created by Dirac as a way to simplify writing out quantum notation instead of writing large matrices everywhere. So we can see that bracket notation scales to multiple qubits. So here we have a set of 2 qubits, 0, 0, 0, 1, 1, 0, and 1, 1. We need to have universality. This is very important. And this is the idea that we can create from a finite sequence of gates, G, as long as they're within an error tolerance. You could build any quantum algorithm from that finite set of gates. This is necessary for any sort of gate generation, which we'll see topologically is done by braid generation. The probabilistic output, this is how we measure the output of a system after it's run through multiple gates, and we collapse the superposition. We can denote this by this operator by the circuit gamma. And the fault tolerance theorem of quantum computing requires many gates can be applied simultaneously to different qubits without affecting the circuit. And then the output is measured by the probability of observing, usually the first qubit, but whatever qubit in this string. And here we have it in brackets. So we see not the complex conjugate, but the conjugate transpose of the subspace W gamma on the projection pi 1, and then W gamma again. So from that we can observe the probability of the output, and then all that comes together in how all of these problems relate to one another, and that is both described in a similar way for classical computing. I don't think it's CQP, but it's also polynomial time. But for quantum, it's BQP, which is bounded error quantum polynomial time. And just to give a quick example, kind of going back to the canonical Shor's algorithm, if we have a binary string of binary digits of certain length, we can say it belongs to a BQP class of decision problems if there's any classical polynomial time in string length algorithm for specifying a quantum circuit gamma y, where the string y satisfies the probability of gamma y being greater than 2/3 if the fy is 1 and less than 1/3 if fy is 0. So over time, we see a statistical probability emerging for our correct answer. So although it's not 1 or 0, the statistical probability of being greater than 1/2 is what ensures that there is a consistent outcome over time. And it's possible from this to construct a single circuit to solve any instance of a given BQP problem of bounded size. And then an example would be if you had n number of qubits, being able to solve for being able to factor integers with, it doesn't have to be less than 1,000 digits, but whatever n number of digits using universal circuit, which simulates all circuits of the size k on n qubits. So we know that there is this requirement for universality and probabilistic input and class of functions that if we can build some form of gate generation for, we have a large class of problems to solve, and hopefully preserve that speed up throughout that entire class. So now we're going to talk about the non-abelian anyons. And I know that I'm a little bit over time, so I will try to speed up, but I really tried to get as much of this into the 20-minute slot, so I'll try to get it done by 30 minutes. So I might need to go a little faster. So the motivation of this is decoherence is common in any modality, and it's quantified by this fidelity distance. Error correcting codes and fault tolerant quantum computing techniques cope with sufficiently small errors by providing some error, by doing error correction within an error magnitude that's smaller than a given accuracy threshold. And the way that you would do this is by implementing logical qubits through the realization, where logical qubits are realized through a multiple of physical qubits. So anything we can do to drive that ratio down is useful. So discussing first the fractional quantum Hall effect. What occurs in a semiconductor in a 2D electron gas when it's placed in a strong magnetic field at very low temperatures? You see a Hall resistance. This is the transverse resistance. It becomes quantized, exhibiting the quantum Hall effect. Here R in the XY plane for the Planck's constant over the electron charge and the electron charge squared filling factor. This filling factor is very important. Initially, this was discussed in terms of integer values. These integer values of the filling factor correspond to Landau levels, which are quantized energy levels of electrons. Importantly, in 1982, Daniel Chiu and I think Horst-Stormer showed that these can also take on fractional values, 1/3, 2/5, 3/7. This can't be explained by non-interacting electrons. Instead, it arises from electron-electron interaction at certain fraction fillings. And this Laflin state, which is one of the more well-known filling factors, could be expressed by this wave function, where we see the position of the electrons positioned in 2D and this magnetic length. What's important is these quasi-particles are all obeying anyonic statistics. When one is moved around another, the wave function picks up a fractional phase, and the FQHE, fractional quantum Hall effect states, are examples of a topically ordered phase, characterized not by symmetry, but by these global topological properties. And this idea of it being a global topological property that's not influenced by local perturbations is critical to the stability of the topological model. So now talking about gap systems and degeneracy. So what was shown in 2003 is that this filling factor 1/3 is threefold degenerate, meaning that a particular energy level has 3 linearly independent eigenstates associated with it, and it exhibits these abelian, in that case, since it was earlier, anionic excitation properties. The movement, when we move excitations around, that multiplies the state factor by this phase factor, and creates these particle-antiparticle pairs. Moving one particle around the torus annihilates it, specifying a unitary operation where probability is preserved. And by moving the particle in 2 different directions, you can obtain 2 different unitary operations that have a commutation relation. And this is important because these are more than a linearly independent state within the same lowest ground state energy, E0. And we'll talk more about that ground state energy level. Also, these systems are gap systems. That means there's a finite correlation length, L0, that local changes only affect nearby regions. These are typical in gap phases of matter. And then these all come together with this topological interaction where the ground state degeneracy on the torus and the excitation of anions are manifestations of the topological properties of this 1/3 filling factor. So it's not practical to use 1/3. You would have to probably implement it as a Q-trit, but 5/2 is more practical. And this degeneracy that we talk about, where we have our independent orthogonal eigenstates, it does get gradually lifted as two particles come closer to each other within that finite correlation length. And we can see how this mechanism works, where 2 to the n-1 dimensional Hilbert spaces split into 2 to the n-2 dimensional subspaces. They correspond to two different types of charge 1/2 particle, which can result from the fusion of charge 1/4 particle. And this is the fusion process where we observe the fusion outcome affects a measurement on the Hilbert space. So this fusion is part of this important measurement process that we're going to discuss. K-code is the idea of essentially a neighborhood. If something is K-local, that means there's that the error cannot produce any coherent transition between distinct code states. It's only undetectable up to a global phase, and that's why this property is important for sufficiently small K local operations, why local perturbations can't split the ground state degeneracy, which provides sort of the core stability of that qubit in that ground state. And then David Gottesman has a theorem on this from 1998, where quantum information in the subspace W can't be degraded by errors operating on fewer than K/2 in the K subspace of the n particles in that K subspace. And these all come together. We talked about anions in 2 dimensions. Braids are these sets of anions, these quasi-particles over time. And I just show a simple 2-dimensional example of these braids evolving. We can have this local Hamiltonian. They can be highly degenerate. And then the ground state G of H is K-code for K in the order of the injectivity radius. So that would be this T of this zone that we're in. And the ground space G is a code subspace, which contains the topological degree of freedom that we are using. Looking at this in 3 dimensions, how do we actually calculate this? This is where that Jones polynomial that I talked about earlier comes in, and the concept of projection. We can see this 2-dimensional representation, the projection of this 3-dimensional over time, yxt evolution of these braids moving through time, moving through space-time. We define HT Hamiltonian with respect to time. The ground states GTI through GTI plus. These consecutive time steps differ by this K/2 local operator. And they're both K-code for O. What's important is this projection of OI onto GTI is unique up to a scalar. This uniqueness property coincides with the notion of adiabatic transport integration in these tautological bundles in these D-planes as we progress up the qubits through time. And then if a Hamiltonian is a closed loop, the projective representation of the braid group is obtained. By choosing H, these can be engineered to be precisely a Heck algebra. I'm not going to go into details of Heck algebra here, but it's how we calculate the Jones polynomial. And then this H was found in 2001 that shared this universality class of the Witten-Schirm's Simon's theorem, special unitary 2 at level 3 for a 4-body Hamiltonian with plateaus at the filling levels 13/5 and 12/5. So braiding, fusing, evaluation. In the spirit of time, I'm probably going to skip this slide, but CS5 is how we is this Chern-Simons 5, which is the special unitary 2 at level 3, the Heck algebra representation, and the batches. We assume n is even if there's a group of anions and n over 2 batches of 4, where each batch B is used to encode 1 qubit complex squared. So, and in this basis, it's mapped to type 0/2 of this twofold composite particle, which results from fusion of a pair of the type 1 particle within the magnetic field. And this is generally the algorithm for our operation of braiding, compilation, adiabatic transport, and projection, where we initialize the system, we give it the problem where we calculate the braids, we have an abstract braid where it's the motion of the anions, and then we measure the fusion outcome and take the projection. Okay, the superconducting indium arsenide aluminum device. How do we actually implement this theory in a real device? I'm going to try to get through this in under 10 minutes. Topological gap protocol device tuning. That's how we set up the device. Modeling this nanowire. We're going to talk about the device geometries. How do we maximize the topological gap? What disorder do we have at the interface? These tetrons, which are the building blocks for starting to build out a large multi-qubit algorithm. And then how input-output was calculated in the most recent paper through an interferometer. So, as we talked about, topological phases are states of matter whose ground state exhibit long-range quantum entanglement. We have these Majorana zero modes. These are topological phases host Majorana zero modes at the ends of quasi-one-dimensional superconducting wires. They're identified experimentally by these zero bias peaks in a differential tunneling conductance. They must remain stable. And then we have a topological gap protocol, which is actually used to tune essentially these zero bias peaks. And this is quite a complex algorithm. There's a whole set of supplemental material for how this is done by the Microsoft team. But the core of the process is you want the ZBPs to appear on both ends of the wire, remain stable, persist across varying magnetic fields. A bulk transport gap is closed and reopening. That's observed. This is this gap system we're talking about. The bulk phase diagram shows a gapless boundary with a gapped interior hosting these stable ZBPs, and then the topological gap exceeds whatever the resolution is needed. This is a 3-terminal device that I'm going to show, and disorder requirements, they require higher mobility, and they also need to be sufficiently narrow. Looking at this device here, we can see sort of a mini model of the system, this nanowire tuned. This is the top image to the one-dimensional topological superconductor. The MZMs are at either end in the stars, and they're depicted by, and then the tunnel couplings between them, the TLTR, form an interferometer, which is indicated by the dashed line and is sensitive to magnetic flux. And then poisoning by quasi-particles in the purple circle that flips the parity, and that's what's detected by the interferometer. In the spirit of time, we can go back to these in the questions. I'm going to continue on. Modeling the proximized nanowire. So this is the Hamiltonian for this system, the simulation of it at least. And to go over the high points, we can talk about any value you want in here in the question section. The proximized nanowire is comprised of a semiconductor nanowire with Rashba spin orbit interactions, which are coupled to the conventional superconductor. The room zero temperature phase diagram of the nanowire consists of the trivial phase and the topological phase. Trivial is and driven as often was what's referred to as the trivial. And they support the latter, the topological supports Majorana zero modes. And the trivial and topological phases are separated by a quantum phase transition. We can see here as Vx mu squared for and then the magnitude of the induced gap induced pairing potential. And the stability of the topological phase is characterized by this bulk transport gap of the topological gap delta T. Some device geometries also we can go further into the diagrams and Q&A, but the core concepts here, 2 device types have been implemented, a single layer gate and dual layer gate designs, consists of an aluminum strip separated from an indium arsenide quantum well by a barrier layer, fabricated in 2 geometries, single layer gate, dual layer gate design, the aluminum strips 10 micrometers long, 120 nanometers wide, 10 nanometers thick, that's why it's 2D. Grounded via large aluminum pads, connected by titanium gold, titanium aluminum leads, and covered by an oxide. And then the electrostatic gate depletes the 2-dimensional electron gas everywhere except beneath the aluminum, and this defines the nanowire. In terms of tuning, we tune the semiconductor beneath the middle aluminum section with an induced gap and magnetic field 0, the wire density is tuned by the middle plunger in the example for, I think, either one or for single layer or dual layer. And more importantly, this optimal regime is reached right before full depletion, where VP is greater than V depletion, in the lowest subband, when the lowest subband is occupied. And then one more point on this, the wire must significantly exceed the coherence length of the phase, so that's about 250 nanometers. This wire's optimal length is 3 micrometers. Materials that are being maximized, generally what we're trying to maximize is large spin orbit coupling and large effective G factor to get a low disorder. Just a couple comments from this, besides some of the values that the single layer device has between 100 microelectron volts and 200 microelectron volts for this induced gap to parent gap ratio. And you can see the normalized G factor here. Just a quick comment on G factors. Generally utilized, it's a dimensionless quantity that's characterized as the magnetic moment and angular momentum. And then the Rashba effect, which we talked about earlier, it's momentum dependent splitting of spin bands in materials in bulk crystals or low dimensional matter. So we're trying to optimize both of those. So how do we deal with charge disorder at the semiconductor dielectric interface? For the topological phase, the biggest issue is there's multiple sources of disorder, but the dominant is the single subband regime charge disorder at the semiconductor dielectric interface. The device geometry is being optimized to minimize the impact of the interface charge, primarily by maximizing aluminum width, pushing to push active indium arsenide regions away from the dielectric interface. We can see the disorder strengths and this correlation length kappa. And why this matters is we can see that we can achieve this from Hall bar measurements of the device, where our peak mobilities that we're seeing of roughly 60,000 centimeters squared per volt second is within is consistent with a measured range between these two orders of magnitude of 6 times 10 to the 4 and 6 times 10 to the 5. And then in terms of expanding this architecture, this concept of a T-tron. So we can see both a linear T-tron and a two-sided T-tron here. We can see the quantum dots, which we saw earlier in that interferometer example, the Majorana zero modes, the topological regions, and then we can see it scaled out in the, and when we extend it to try to do coherent operations. This has not been shown experimentally yet. This is something I'm going to talk about at the very end. To support measurement-based grading, the two-sided T-tron consists of two superconducting islands, each with a topological segment separated by a trivial link. And this architecture supports a unitary Clifford gate, as well as other quantum gates via a sequence of single and 2 qubit measurements, with 1 qubit serving as a ancilla bit, which for quantum computing is important because we need to have reversible, we require reversible operations. And then all of these have to be tuned every single time with a topological gap protocol to get those Majorana zero modes properly tuned in the device. So doing that topological gap protocol efficiently is an important part of this architecture. And then a couple of topics on the most recent paper from Microsoft on their measurement on fermion parity and the interferometer that we saw earlier at the beginning of the section. It's a triple quantum dot device. Fermion parity is a conserved quantum number, describes whether a system contains an even or odd number of fermions in the absence of quasi-particle poisoning. Fermion parity is conserved. Fermion parity shared by a pair of Majorana zero modes can be determined through an interferometer. The interferometer shown in the topological, sorry, not that protocol, device tuning is composed of the nanowire that will have Majorana zero modes at its end. And then the most important probably bullet point here is the output of the interferometer is encoded in a quantum capacitance, a complex quantum capacitance in the second quantum dot, which is measured dispersively via a resonator circuit And this is probably some of the complexity of the supplemental material of this paper. And it yields a time resolve capacitance trace, which records the parity dynamics of the system. You sweep the dot gate voltage and the flux. You obtain this dependent bimodal distribution, CQ, and the peaks are separated by this delta CQBX, which is on the next figure, and this oscillation period. And that oscillation is consistent with the expected flux of Planck's constant over 2E. And through the interference loop in the device geometry, we interpret that as a random telegraph signal, and CQ then we believe it's originating from switching of the fermion parity of the wire. And this is sort of a quick explanation. Probably the most important figure here is, I think, H and I, where we show a bimodality, looks sort of like an eye diagram, that is the flux dependent with this period of H over 2E, and the vertical arrow indicating the BX values at which the time trace in the panels A and B are taken. Okay, I'm sorry for going over the 20 minutes. I know that was a little bit longer, but I tried to cover everything. One final point before I do the Q&A. So the most recent paper made a very clear statement. This is the 2025 interferometer paper, that these measurements of the interferometer by themselves determine whether the low energy states detected by the interferometer are topological. Sorry, let me state this clearly. The measurements from the interferometer do not by themselves determine whether the low energy states detected by the interferometry are topological. That is still an open question effectively. Part of that is because fusion has not fully been shown in a multi-Tetron device, but they also state that they have highly constrained their allowable energy splittings for the models of trivial and Dreven states. So it is tightly constrained, but they're not claiming in this paper that they have fully demonstrated the low energy state being topological. Okay, thank you so much for listening. I will take questions you have at this time. Also, would you prefer me to stop the recording or keep the recording going?
Thank you, Joseph. I think by university regulation, we need to stop the recording.
Okay, and, yeah. I will stop the recording then.
Yes. Thanks for everyone coming. Joseph is a good student. He started his PhD back in George Washington with Dr. Soldier, and then now he's working toward the quantum. I think he presented quite a well description, and now the floor is open for the Q&A.